Hello, students. Tell me one thing. Are the walls of your room moving right now? You'd probably say, no, sir, obviously not. They're fixed to the ground. But just think about it for a second. If you get up and start walking towards one of those walls, isn't that wall coming closer to you? From your perspective, that distance is decreasing, right? Suddenly, your whole basic idea of reality and stillness completely shifts. And that, my dear students, is the absolute magic of physics.
Welcome to today's Explainer. I am so thrilled to have you in my class today. We're going to unlock the hidden rules of motion. Think of me as your senior physics teacher, and together we are going to uncover the universe's most beautiful geometric secrets. We aren't just going to memorize boring formulas. No, we are going to actually feel the physics happening all around us. So here's our lesson plan for today. First, we'll look at the illusion of rest. Second, the different kinds of motion. Third, the big battle between distance and displacement. And finally, speed and velocity explained. Let's get right into it. Section 1, the illusion of rest. Before we go any further, we really need to define what exactly we're studying today, and that is kinematics. What's really interesting here is that we get to act like geometric detectives. You know, we often think of objects as just sitting there doing nothing, but as you'll see, stillness is mostly just a trick of the mind. In kinematics, we only study the movement itself. How far did it go? How fast did it move? We absolutely do not worry about the forces pushing or pulling the object or the energy spent. We leave the why for later and focus entirely on the how. So the most crucial point to understand is that rest and motion are relative terms. They are not absolute. Let me ask you a very simple question. When you sit inside a moving train and look out the window, does the station come to you or do you go to the station? Well, from your perspective inside the train, the station is rushing right towards you. For motion to happen, you always need a reference point. If your position changes with respect to a reference point as time passes, you are in motion. If it doesn't change, you are at rest. Simple logic, right? Section 2, different kinds of motion. Now, there are 4 main categories of movement in space. First is translatory motion. Just imagine a car driving down a straight road. All parts of the car move together, right? Second is rotatory motion. Think of a spinning bicycle wheel rotating on its fixed axis. Third, we have periodic motion. This is motion that repeats in a strictly fixed time interval, exactly like the hands of a clock completing a circle every 60 seconds. And finally, oscillatory motion, which is this wonderful back and forth or to and fro kind of movement. Let's actually look a bit closer at that last one. To perfectly illustrate oscillatory motion, let's imagine a simple pendulum right here in our classroom. You've probably seen these on big old grandfather clocks. Step 1, the little weight at the bottom, which we call the bob, moves away from its center resting spot, its mean position. Step 2, it gets pulled back towards the center. But then, step 3, it doesn't just stop. It flies right through to the other side, back and forth, back and forth. But why exactly does it do this? Well, the secret lies in 2 very powerful concepts. The first one is the restoring force. As the bob swings further away from the center, this invisible mechanism acts almost like a strict teacher, constantly attempting to pull the pendulum bob right back to its center equilibrium. It desperately wants the bob to just be at rest in the middle. But opposing this is our second concept, and that is inertia. While the restoring force brings the bob back to the center, inertia is the rebellious property that ensures the bob continues its swing to the completely opposite side instead of just stopping abruptly. It's basically the physical rule that says, hey, I am already moving, so I want to keep moving. Together, this restoring force and inertia keep this beautiful geometric dance alive. Section 3, distance versus displacements. Now we face the ultimate battle. Distance versus displacement. See, distance is just the total path length you covered. It doesn't care which way you went, it just adds up every single step. We call this a scalar quantity in physics. But displacement is very strict. It is the absolute shortest straight line path from your starting point to your finishing point. It cares deeply about direction. We call this a vector quantity. Let's visualize this to make it super clear. Imagine a little ant walking 4 meters completely east, taking a 90-degree left turn, and then walking 3 meters exactly north. What is the distance? Simple addition. 4 plus 3 equals 7 meters. But what is the displacement? The displacement is the direct, straight line from the start to the finish. Since this forms a right-angle triangle, we can just use our trusty Pythagorean theorem. 4 squared is 16, 3 squared is 9. 16 plus 9 is 25, and the square root of 25 gives us exactly 5 meters of displacement. Notice how much smaller the displacement is compared to the total distance. Let's try another little geometric puzzle to really lock this in your minds. Imagine a bicycle tire standing upright. A bug starts at the very bottom and walks exactly halfway around the curved edge to the very top. What is the distance? Well, the distance is that curved semicircle path, which geometrically is pi multiplied by the radius. But the displacement? The displacement just cuts straight through the empty air from the bottom to the top. It's just a straight line, the diameter of the circle, or 2 times the radius. So, let me ask you a trick question. Listen carefully now. Students, what is your displacement if you travel 60 kilometers all the way to your school and then return back to the exact same spot at home? Think about it for a second. Your distance is 120 kilometers, but your displacement? It's 0. A big, round 0. Why? Because your starting position and your final position are the exact same point. The shortest distance between where you started and where you ended up is 0.
Section 4. Speed and velocity explained.
Now that we have fully mastered distance and displacement, let's add the element of time into the mix to unlock the next level of kinematics. Just as distance and displacement are siblings, speed and velocity are their direct cousins. Speed is simply the distance you traveled divided by the time it took. It is a scalar, just like distance. But velocity? Velocity is your displacement divided by time. Because displacement has a direction, velocity also has a strict direction. That makes it a vector.
And this brings us to a really fascinating paradox in physics. You can have an incredibly high average speed, but a velocity of absolute 0. How is that possible? Well, go back to our school example. If you drive 60 kilometers to school and 60 back really, really fast, your average speed is very high. But because your total displacement is 0, when you divide that 0 displacement by the time taken, your average velocity for the whole trip is wiped out entirely. It is absolute 0. Now, we've talked about maintaining a speed or a velocity, but what happens when you press the gas pedal in a car, or hit the brakes, or maybe take a sharp turn? Your velocity itself changes, and in physics, whenever velocity changes, whether you are speeding up, slowing down, or changing your direction, we experience the ultimate concept of kinematics, which is acceleration. But that, my students, is a beautiful topic for our very next class together. As we wrap up today's explainer, I want you to look around your room again. Think about the motion happening all around you, from the hands of a clock to a moving car outside, even the Earth spinning on its axis. Is every single step you take just a part of this grand, hidden, geometric dance of the universe? I hope today's masterclass has sparked a real curiosity in you to observe the kinematics in your everyday life. Keep questioning, keep observing, and I will see you next time.